So this is a circuit for teleportation. Now what I want to do is take this circuit for teleportation and use it to show you that teleportation works. And this involves doing a bunch of, I guess, operations on circuits which leave what the circuit does unchanged, but, make it clearer, or at least. Yeah. But first, what did I want to do? First, I wanted to divide this into Alice and Bob. So Alice has the first two parts. So the first operation, if we take plus and 0 and apply a control not, we get 1 over root 2, 0, 0, plus 1, 1. So that means that the circuit is equivalent to 0 plus 0. I'm going to put a control not here, and then a control not here, and then a Hadamard, and then a measurement, and a classically controlled, well, two measurements, and a classically controlled X, which I guess I should be drawing in green. And a classically controlled Z. So this does the same thing as this circuit. So if you can prove that this one teleports, you can prove this one teleports. Okay, now the second change I want to make in the circuits is moving these controls to the left of these measurements. So what does that look like? Okay, we're starting with our unknown qubit. Yeah. Our unknown qubit was supposed to be zeta. And I seem to have renamed it in the first picture, so let's fix that. Zeta, and a plus and a 0. And the first thing is a control not here. The second thing is a control not here. And then there's a Hadamard up there. And then there's Control Z, Control X, and a measurement here. And a measurement here. Let's see. Okay, good. And I really should have. Okay, so what did we do? What we're saying is it doesn't matter if we do this measurement and then do the control classically, or if we just do a quantum control knot and then do the measurement. So why is this true? So we have a unitary. We have a qubit here, say. And we have another qubit here, alpha 0 plus beta 1. And we want to say that a control knot before a measurement is the same as a classical measurement, followed by a controlled knot. Well, alpha z, or alpha 0, 0, 1. So this is actually not the most general situation, but I'll just show you what happens in this situation. Phi, and we want to do a C naught on this is equal to alpha 0, and the C naught does nothing if alpha is 0, plus beta 1 sigma x phi. So doing a control knot on this gives you alpha 0 phi plus beta 1 sigma x phi. Measuring zero. If you get 0 as a result of the measurement, you have alpha phi. And if you get 1 as a result of the measurement, you have beta sigma x times phi. Now, if you measured first, this should be alpha squared. I'm sorry. And beta squared. Now, if you'd measured first, with alpha squared probability, you would have gotten 0, and with beta squared probability, you would have gotten 1. And then when you apply the controlled classical sigma x to phi, you get, with probability alpha squared, you get phi, and with probability beta squared, you get sigma x phi. So in this case, these two results are the same. And in fact, the two results are always the same, and you can show it with a little more computation in quantum computing. Yeah, you have a question?
What specifically do you mean by they're always the same?
Oh, well, if you have a measurement, and a basis, well, if you have a controlled unitary followed by a measurement in this basis, it's the same as first doing the measurement and then doing the classically controlled unitary. The results here, the probability of the probabilities you outcomes for the measurement and the quantum states at the end of the measurement will be identical. Okay, so now our original circuit was equal to this. And now there's only one more step we need to take to get the circuit. Well, actually 2 steps. A controlled z is equal to a controlled z up. So they both give unitary one, 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 minus 1. So this is just saying change this phase of the entire system if both the top and bottom qubits are 1, because you do nothing if the top qubit is 0, and if the top qubit is 1, you change the global phase. You change the phase only if the bottom qubit is 1, because sigma z was 1. Sigma z was this matrix 1 minus 1. But this matrix is symmetric in the first qubit, so it's the same as this thing. And a control z is equal to a control x, Hadamard, Hadamard. Because z equals h sigma x h. So if you put a control on them, you still get the same identity. So what we're going to do is we're going to take this and we're going to turn that over. And let's do it up here. Zeta. Plus 0. Okay, there's an h here, and there's another control knot here, and then a control knot up this way with an h on the left and an h on the right. And yeah, okay, good. And the last transformation we need to do is just, remember, if you apply 2 h's, they give the identity. So this is completely equivalent to our teleportation circuit. Of course, now we have control knot gates between Alice and Bob, which weren't present in the original, but that doesn't matter for the analysis.